All right, guys. So this is to help us with a couple different things that were on our test review that has to deal with atomic radius, electronegativity, ionization energy, and ions. So first thing let me do is shift this up and flip this over real quick. Okay. Zoomed out as much as we can be. I guess so. All right. So an ion is a non-neutral atom. Neutral atoms have the same number of positives as negatives. So non-neutral means there's going to be an imbalance. There's going to be a different number of electrons than protons in this. So it's going to have either a positive or negative charge. So an ion can become positively charged if it loses one or more of its valence electrons, the electrons in the outermost energy shell. So for example, right, if something had 10 protons, 10 electrons, positive 10 and a negative 10, 0, neutral. But if it wound up having 9 electrons, well, a 10 plus a negative 9 equals a positive 1. So it would have a positive 1 charge. Those would be like your alkali metals. Your alkaline earth metals usually have a tendency to lose 2 of their valence electrons. So let's just say, for example, okay, we had 10 protons, and an element now has only 8 electrons. All right, 10 plus a negative 8 is going to be a positive 2. It would have a positive 2 charge. Most of your metals, left side of the periodic table, are going to form cations. Anions, or how something can become negatively charged, it's going to gain 1 or more valence electrons. Now these are going to be mostly your non-metals. So left or right of the staircase, your nitrogens, oxygens, fluorine, sulfur, phosphorus, chlorine, okay? Those guys, the halogens in group 17 or group 7A, depending upon your periodic table. For example, 8 protons, 8 electrons, neutral, no charge. 8 protons, but it winds up having 9 electrons, then it would have a charge of negative 1. If it had 8 protons, and then we said, okay, well, it has 10 electrons, 8 plus a negative 10 is going to be a negative 2. It has a negative 2 charge. So if we just go back to our periodic table really quickly. Remember that valence electrons only occur from the S and P sublevels. All right, so these guys in group 1 have 1 valence electron. Group 2 is 2 valence electrons. Group 13, all right, think about going across. Only the S and P count for it. So 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So 8 is the maximum amount of valence electrons that you can have in every energy level except the first principal energy level. Helium can only have a maximum of 2. But everybody else wants it to be 8. So let's say sodium, for example. Sodium has 1 valence electron. All right. So this guy is going to wind up having a tendency of losing an electron and going backwards to have a noble gas configuration of the noble gas that came before it, which would be your neon. So what is ionization energy? And how are these things kind of happening? So an ionization energy is the energy needed to remove an electron. Well, valence electrons specifically. For sodium, it only has the 1 electron, so these guys have a tendency to give up their outermost electrons relatively easy. The noble gases, though, there's like an octet rule where you have a completely filled at highest energy level. So 1, 2, 3, 4, 5, 6, 7. If that is completely filled, it is the most stable thing that the atoms have, and they don't want to change. Is it possible to remove an electron? Yes, but it takes an extremely large amount of energy. So these guys do have an ionization energy. It's very, very high. Guys on this side, nah, not so much. Because sodium would be like, all right, if you take my one electron, my one valence electron, well, now my configuration, my electron configuration, if we drew that out, would be the exact same as argon, and it's nice and it's stable. Magnesium. Oh, you want to take both of mine? Okay, sweet. All right, I would go backwards. Sorry, not argon, neon. It would go back to being like neon. Same configuration there. Because it would be easier for it to lose those 2 electrons than try and gain, all right, another 1, 2, 3, 4, 5, 6 to become a complete 8. So ionization energy winds up increasing as we go across because fluorine, the amount of energy to remove a valence electron, well, to remove 7 doesn't make sense. So it has a very, very high electronegativity. And its valence electrons are pretty close overall to the nucleus. Now, as we get down a row, as we go down a column, as we go down a group, what happens to an atomic radius? The atomic radius, what happens is every time we go down an energy level in a group, you're adding on essentially an extra shell. And those valence electrons are now farther away from the nucleus. So as we go down, remember the atomic snowman? The atomic snowman, if you think of how a snowman looks, as you go down, there's more and more energy shells. So the atoms are going to get larger as they go down a group. What happens is, as we go across, there's no more outside energy shell. If the valence shell is no longer going to, add on. So the shielding effect isn't as strong once we have more protons being added. They're going to be able to pull on the outside valence electrons a little bit better, so they're going to decrease. So that is our trend for atomic radius. All right. Gets bigger as we go in this slanted direction. If we were looking at our periodic table, well, here's our periodic table. All right, so it gets bigger as it kind of slants down over towards francium. Francium would probably be our biggest guy. The other two are the opposite. So if you know that the atomic snowman is this way, okay, gets bigger as it goes down, smaller as it goes across. The ionization energy and electronegativity are the opposites of that. So the strongest, all right, the way they go, if you're looking kind of how that arrow points, okay, starts kind of weak down here and gets stronger as we go up this way. So if you were comparing a couple different elements, you could use those trends in order to tell someone whether or not who has a higher energy, ionization energy, or a higher electronegativity, or a greater radius. So here will be I'll name an example. So which of the 3 items or elements that I'm going to name, which of those 3 has the highest ionization energy? All right, so remember, ionization energy's trend goes like this. Let me straighten this out. All right, it increases as it goes in that direction. So let's name the 3. Let's go with, sorry about that. Let's go with tin. Let's go with arsenic. Let's go with sulfur. All right, so the atomic radius increases on the way down, decreases over here. They're the opposite. So again, for ionization energy and electronegativity, it's this way. All right, it's this way. And why ionization energy is so strong towards this way? Well, the valence electrons are very, very close to the nucleus as we go up this way because the atoms are smaller. So the neutrons, I'm sorry, the nucleus has a stronger attraction to those valence electrons. Plus, it's not going to want to remove those 7. So definitely not gonna happen here. And why they have such strong electronegativity? Electronegativity is the ability to attract an electron. All right. Well, 7 pretty much. Hey, how many valence electrons do I need to become a complete 8? I just need the 1. Oxygen would need need 2, so it has a pretty strong electronegativity. These guys that are over here are very, very weak. Why? Because it would need to say like, oh, I need to gain 7. That's really, really difficult to do. I can't do that. So these guys over on this way have a lower and weaker electronegativity and ionization energy. Guys over in this general direction, all right, going up in the slant to the right, have a higher ionization energy and electronegativity. So out of these 3, higher ionization energy going to be your sulfur, based off of just those 3. Okay, if you said in the same group, all right, if we decided to go in the same group, how would that work? All right, let's say we did chlorine, bromine, and iodine, those 3. Well, the atomic snowman is down, gets bigger, gets smaller as we go this way. So these guys would be the opposite. It gets stronger as we go up. So chlorine would have the greatest. What about if they're in the same period, which is a row? If they're in the same period, let's go with arsenic, so sulfur and, phosphorus, sulfur, chlorine. Again, going across a row for ionization energy and electronegativity, chlorine is the stronger of these guys out of those dudes. Now, atomic radius is different. Bigger as we go down, smaller as we go across. So that dude, if we look at this, let's get the blue color here for our radius. That is not blue. Is that blue? I don't know, it's close enough, no? There we go. Alright, so we're going to do, well, bam. Right, so our radius here, it's kind of how our radius works. Gets larger as we go down, smaller as we go across. So any of those options that we had just looked at, all right, would have been in the opposite of our electronegativity and ionization energies. Yeah, so those are our trends, and that would be how you kind of can pick out, all right, different options. So if I said, okay, atomic radius real quick, we'll just do a brief example of potassium, germanium, and bromine. Bromine. Who has the greatest radius? Well, remember, as we go down, we get extra energy levels, outside shells. But as we go across, we don't add any extra shells. All right, we have our inside dudes here. The shielding doesn't really work as much, so they're going to get smaller as we go across. So francium would be our largest guy. Hydrogen is our smallest, but this happens to be kind of the natural trend here. Okay. Hopefully, guys, that helps.